control. Okay, I'll start now. There's no streaming tonight. You may have seen our Scott's sick, so the only people who will see this are the people that are here tonight. So welcome to Astronomy Education. I'm Colin Hill, and tonight's talk is on stellar evolution part 2. So for those who were here last month, I did part 1, which was on the Hertzsprung-Russell diagram. So there will be a slide on that in this talk as well, so there'll be a brief recap on that for those who missed it last time. Before I start, I'd like to acknowledge and pay our respects to the Gawler people, the traditional custodians whose ancestral lands we gather on. We acknowledge the deep feelings of attachment and relationship of the Gawler people to country, and we respect and value their past, present, and ongoing connection to the land and cultural beliefs. Right, so this talk will basically take us from star formation all the way through to stellar death in the form of a white dwarf or a supernova. So how a star is born? So you need some sort of basic ingredients to make a star. So that basic ingredients comes in the form of molecular clouds containing hydrogen and helium. So the galaxy is full of molecular clouds, but a molecular cloud on its own won't do much. It'll just sit there being a molecular cloud. It needs a trigger to start star formation. And those triggers can be in the form of perhaps a density wave. So all spiral galaxies have a density wave traveling around them, and that's what gives them the spiral appearance. And as the density wave travels through the dust and gas, it causes compression of the dust in the clouds, the molecular clouds, and this can trigger star formation. So that's why the spiral arms in a spiral galaxy are illuminated by the hot blue stars that have been born as the density wave travels through them. If it wasn't for that, you wouldn't even be able to see the spiral arms at all. Another way to trigger stellar formation is supernovas. So when a supernova explodes, it puts a shock wave out, and if it happens to be near a molecular cloud, that can trigger star formation. Or a galactic collision. So this is more dramatic, but it does happen. Galaxies do collide, and when they do, there's huge bursts of star formation. So you can see here, there are two galaxies colliding, and you see there's lots of blue areas here where new stars have been born when the gases of the two galaxies sort of crash into each other and compress. So when you have all these factors together, you can end up with a star or lots of stars. So here we have a protostar that's been born through the gravitational collapse of gas in the cloud, and with a circumstellar disk around it of material, and it's this material that ends up forming the planets and moons around the newborn star. So when a star's first born, it enters what's called the T Tauri phase after the prototype of the type of star T Tauri. So a T Tauri star is basically a protostar. It's not generating energy through nuclear fusion as yet. So it's the first stage of a star's life. They're very unstable and highly variable, and they're powered only by gravitational contraction only. The cores of these stars aren't hot enough for nuclear fusion to have started. And they've got these huge sunspots on them, and that's one of the reasons why they're quite variable as the sunspots rotate on the rapidly rotating star. And they're surrounded by a disk of dust and gas, as from like on the previous image, from the nebula in which the star was formed. Okay, so I'll just have a little bit of a run through on basic nuclear fusion, so you can appreciate how a star like the sun produces all that energy. Now a solar mass star produces its energy through what's known as the proton-proton cycle. Heavier stars, more massive stars do it in a different way, which I'll go through in a moment. So basically, the way it works, in the core of a star like the Sun, at a temperature of about 15 million degrees, all of the hydrogen is in the form of a plasma. So there's no atoms. All the electrons have been stripped off the nuclei, and we just have free protons flying around at high speed. And every now and again, we'll get two protons that'll collide and fuse together, hence the name fusion. And when they do so, they form a nucleus of deuterium. Deuterium is a heavy hydrogen. So it's hydrogen with a hydrogen nucleus with a neutron attached to it. In the process, it gives off a neutrino. Now, neutrinos don't interact very much with matter, so the neutrino goes flying off through the star, almost unimpeded. It also produces a positron. Now, positron is an antimatter electron, and antimatter doesn't like normal matter very much. So when a positron meets an electron, they instantly annihilate each other and give off a gamma ray. So this is energy. So that energy is then radiated away from the core. Sometime later, another free proton may fuse with the deuterium nucleus, forming a nucleus of helium-3, which is a light version of helium. In the process, it gives off a gamma ray, more energy. Sometime later, two helium-3 nuclei may fuse to produce a helium-4 nuclei, and this produces two free protons, which can then be used in further reactions, and another gamma ray, more energy. So in this process, there's a 1% mass loss, and this mass is converted into pure energy through Einstein's equation E equals mc squared. So if you've got mass, the mass that was converted is that 1%. If you multiply that by the speed of light squared, you end up with an enormous amount of energy. So this is why nuclear fusion creates so much energy, because it actually converts matter into energy. Just to sort of give you an idea of how much energy matter contains, if you had a 1 kilogram mass, it could be anything, say a lump of coal, 1 kilogram lump of coal. If you converted that into pure energy, there would be enough energy produced to power our entire planet for a few months. That's how much energy is locked up in normal matter. So even though it's only 1% of that matter is converted into energy, it's an enormous amount of energy. So in a star like the Sun, it's consuming around about 400 million tonnes per second of hydrogen. And of that, 4 million tonnes is converted into pure energy. So I said I'd do a bit of a recap on the Hertzsprung-Russell diagram. So for those who weren't here last time, it's a plot. You can put any star and you can plot it somewhere on this diagram. So on the bottom here we have surface temperature, ranging from about 2,500 degrees up to 50,000 degrees Kelvin. And on the vertical axis we have luminosity. So if we use the Sun as 1 down here, so there's the Sun, and you can come down here and there's the temperature of the Sun, about 6,000 degrees or so. And so stars that are less luminous are down here, and stars that are more luminous are up here. And then this is the main sequence, which are stars that are burning hydrogen in their cores, like most stars do. Up here we have the red giants, which we'll talk about later. These are stars that have run out of hydrogen and are burning heavier elements. And down here we have the white dwarfs, which are the cores of burnt out stars. So when the solar mass star, like the sun, runs out of hydrogen after about 10 billion years or so, fusion in the core shuts down and continues in a shell around the core. So in a main sequence star, like the sun is at the moment, we have the hydrogen burning core and is the extended envelope around it. But when it runs out of hydrogen, we have an inert helium core. So helium is like the ash from the hydrogen fusion. So we have an inert helium core with a hydrogen burning shell around it. And this produces an enormous amount of energy, which puffs out the outer layers, and the star expands and cools off as it does so. And so it goes from like yellow, like the sun, to red. So, and it's much bigger, so that's why it's called a red giant. Now the core contracts under gravity and heats up, and this also adds extra heat to the reaction. So when this happens, the star then moves off the main sequence and moves up to the upper right of the HR diagram to where we saw the red giants before. So now eventually, the helium core, under the constant gravitational contraction, reaches about 100 million degrees. And this is the ignition point of helium. So at this point, the helium starts to fuse into carbon and oxygen, and surface temperatures begin to rise again. Now, helium burning is not as efficient as hydrogen burning. So it only lasts for about 100 million years, as opposed to 10 billion years with the hydrogen fusion. So eventually it runs out of helium in the core, and the core again shuts down. Then helium burning moves out to a shell around the inert core. So we end up with a situation like this, where we have an inert carbon-oxygen core with a helium burning shell around it, and above that, a hydrogen burning shell, and above that, the extended hydrogen-helium envelope. At this point, it becomes what's called a horizontal branch star. So on the HR diagram, there's a region in the upper right, which is a horizontal branch of these evolved stars like this, at this point in their lives. So we ended up to the end game now for a solar mass star. It starts to pulsate, and in its death throes, it'll throw off the entire outer envelope into space, and it becomes, it turns it into a planetary nebula, like the dumbbell or the helix. So, so the helium shell, because it's not as efficient, it burns the fuel quicker than the hydrogen shell can supply it with fuel. So what was happening is that hydrogen shell is converting hydrogen into helium. The helium sinks into the helium shell, and that supplies it with fuel. But the helium shell is burning it quicker than the hydrogen shell can supply it. So it keeps shutting down and restarting all the time. And this is what drives these pulsations. So yeah, so the helium shell shuts down until fuel builds up, and then it reignites. And this can happen 4 or 5 times, yeah, like that, until finally it blows off the entire hydrogen envelope, and producing these beautiful planetary nebula in the process. Now, planetary nebula have got nothing to do with planets. The name comes from a time when they first looked at these objects in telescopes, and they thought that they looked like planetary disks, because a lot of them were very small and greenish, and it looked a little bit like looking at Uranus or Neptune in a telescope. So that's where the name comes from. And at the centre, there's a super dense, very hot core, the the inert, super dense, very hot core becomes a white dwarf star. So if you have a look at these images here, you can see there is a central star there and there. So this is the core remnant of the dying star, and that it turns into a white dwarf, which is only about the size of the Earth, but has about half a solar mass packed into it. So as you can imagine, that's incredibly dense material. A teaspoon of it weighs about a tonne. Now, what happens to more massive stars? Now, above about 1.3 solar masses, fusion occurs in a different way. It goes through what's called the carbon, nitrogen, oxygen, or CNO cycle. It uses these elements as more of a catalyst. It's only a means to an end. It still produces helium at the end, so it starts up with hydrogen and it finishes up with helium. And it just sort of uses these as a catalyst to do that. So we have hydrogen that will combine with a carbon nucleus producing nitrogen, giving off a gamma ray. And then it decays back to carbon again, giving off a neutrino and a positron, combines with another proton, producing nitrogen again, different isotope. This is nitrogen 14 instead of 13. When that decays, it produces oxygen, fuses with another proton, produces another gamma ray, decays to nitrogen 15 this time, producing another neutrino, another positron, and then it combines with another proton to finally produce helium again, at the end, helium, and back to carbon 12 to start the process over again. A little bit more complex than the proton-proton cycle, but it ends up doing the same job, converting hydrogen into helium. And the reason it uses this process is because in more massive stars, the core temperature is higher. So that's why this process tends to dominate over the proton-proton cycle. So what happens after the CNO cycle? Well, if a star is greater than about 8 solar masses, it goes through this process. So like a low mass star, it'll start off fusing hydrogen at 20 million Kelvin. And for a 20 solar mass star, this only lasts for about 10 million years. So you can see here, for a more massive star, because of the higher core temperature, it chews through the fuel much more rapidly than a low mass star. So even though it's got more fuel to start with, it consumes it at a much, much greater rate. So it chews through that hydrogen in about 10 million years, which is about 1,000 times quicker than the sun. Once that runs out, it starts to fuse the helium in the core at 100 million degrees. This lasts for about 1 million years. When that runs out, because it's a more massive star, it's able to produce much higher temperatures in the core. So with a solar mass star, it doesn't get hot enough to fuse carbon, but in a high mass star, it does. So at 600 million degrees, carbon starts to fuse into into neon and magnesium. And that only lasts for about 1,000 years. And at 1,500 million degrees, the oxygen starts to fuse into silicon. And this only lasts for 10 years. Finally, when that runs out, the core gets up to 4 billion degrees. And at that temperature, the silicon starts to fuse into iron. And this lasts for 1 day. It really chews through that fuel, and it builds up a core of iron, Fe, iron. Now, iron is the most stable element on the periodic table. The only way you can fuse iron into heavier elements is to put energy into the reaction. So it all stops. All fusion stops at that point. And that's when the delicate balance between energy and gravity is finally lost, and the star will collapse. So, and we get a supernova. So silicon fusion produces iron, which cannot be fused to produce any energy. And when the iron core reaches about 1.4 solar masses, it gets to that critical mass that it can no longer support its own weight. And it implodes within a second. So the entire iron core collapses down to nuclear density in about a second. So that's like the entire iron core becomes about the size of Adelaide. When it does that, it rebounds. Like it actually goes more massive than nuclear density, and then it rebounds. And that rebound puts the shock wave travelling back up through all the outer layers which are crashing back into it, meet this shock wave going back the other way. And that drives the supernova explosion. And the energy released in the explosion is more energy than the sun produces in its whole 10 billion year lifetime. But 99% of that energy is released in the form of neutrinos. Most of the neutrinos pass right through the star almost unimpeded, but there are so many of them that they actually help drive the explosion. They've done some modelling and they realised without the neutrinos, the explosion would stall before it reached the surface of the star. But with the neutrinos, helps drive the explosion and to reach the surface, and the star then explodes. And the remaining 1% is released as heat, light, and other radiation. And the core remnant, so that collapsed core, is usually a fast-spinning neutron star or a pulsar, but maybe a black hole if massive enough. So if the mass of the star was greater than about 50 solar masses, it may produce a black hole. And it's actually called a hypernova because these are particularly powerful explosions when they occur. So when a supernova goes off, it can be brighter than the whole host galaxy of, all 400 or 500 billion stars all combined. It can outshine all those for about a week or two. And many heavy elements are created by the explosion, which are later recycled into new stars and planets. So in the actual explosion itself, this does have enough energy to fuse iron and other elements, and there's a lot of then radioactive decays occur. So this is where elements like gold, lead, platinum, all these heavy elements, this is the only place in the universe that these heavy elements are actually created, the elements heavier than iron. But there are various types of supernova, and it's a little bit confusing. We have type 1s. Type 1 supernova, the definition is hydrogen not present in the spectrum. So a type 1A is a totally different type of supernova to what we just discussed. It's caused by a white dwarf star orbiting very closely to an evolved companion, so a red giant. So it's a binary system, but in a very close orbit. And a white dwarf has got a very, very powerful gravitational field because it's a collapsed star. So it pulls gas off the red giant, and it forms an accretion disk around the white dwarf, which slowly spirals in and lands on the surface. Now, this builds up a layer of hydrogen on the surface of the white dwarf, and it reaches a critical density and mass where it goes into a thermonuclear explosion, basically. It's like a hydrogen bomb goes off on the surface. And the white dwarf can then brighten by about a factor of 1,000 during this explosion. And the main talk tonight will actually discuss a nova. So this is a nova explosion, not a supernova. So it doesn't destroy the star. The star will then settle down and begin accreting hydrogen again. So we can have recurrent novas, and that's also the topic of the main talk tonight. Well, one of the main talks tonight is recurrent novas, and one that we're supposed to be seeing now, but it hasn't occurred yet. Then we have type 2 supernovas, where hydrogen is present in the spectrum. And so this is basically the type of supernova I just discussed earlier, which is an iron core collapse supernova. Now, these are more powerful than a type 1a, but they're fainter, which seems contradictory. But that's because most of the energy of the type 2 is produces neutrinos, which we can't see. Whereas most of the energy in a type 1a is in the form of electromagnetic radiation, which we can detect. And this is where it gets confusing, because we have a type 1b. So it's a type 1 because hydrogen is not present in the spectrum, like a 1a. But it's the same mechanism as a type 2. So it's the explosion of a massive Wolf-Rayet star. So these are massive stars that they produce so much radiation that they're actually blown off their hydrogen envelope just by sheer energy. Blowing the solar wind that they produce actually strips out the whole hydrogen layer off the star and leaves the helium burning core exposed. So when they finally explode, there's no hydrogen there in the spectrum. So that's why it's a type 1b. But the explosive mechanism is the same as a type 2. Then we have a type 1c, which is the same as a type 1b, but the helium envelope is also missing. So these are stars that have also stripped away all the helium as well and left the carbon shell exposed. So this diagram here shows an example of a Wolf-Rayet star, and it's producing this envelope of gas. So this is the gas that's blowing off due to its own energy, expelling its outer layers into space. So you can probably gather from this that mass governs the stars. So if you have a look at this table here, down here on this line here, we have the sun. The sun is one solar mass, and it will live for about 10 billion years, and obviously it has a luminosity of 1, if the sun equals 1. Now for a star that's only a tenth the size, a tenth the mass of the sun, like a red dwarf, it'll live for up to or greater than 1 trillion years. So no red dwarf has actually lived long enough to have actually died in the life of the universe. Every red dwarf that has ever been born is still burning away hydrogen. But they have very, very low luminosity. So that's 0.1% of the solar output. And because of that, no red dwarf is visible to the naked eye. Even though 75% of all stars are red dwarfs, there's not one single red dwarf that's visible to the naked eye in the night sky. not even close. Then, as we increase in solar mass, as we go up in solar mass, you can see the lifetime gets shorter and shorter and shorter until we get up to 150 solar masses, which is about as heavy as a star can get. They haven't found any stars heavier than that. But they only live for about 500,000 years. So, as you can see, they're very rare, because not only do very massive stars, not very many of them are born, they don't live very long either. So stars of this mass, there's probably only 20 of them in the entire galaxy of 400 billion stars. But look at the power they put out. These stars are putting out millions of times the luminosity of the sun. So the ones that are out there, we can see them even though they're at tremendous distances because they're just so luminous. And that concludes the talk. Any questions? Must have covered it pretty well. Yes, Werner?
When you start off with the T-Tauri phase on the fairly white field star, when the ignition occurs, I'm assuming these T-Tauri stars, protostars, will be visible?
Oh, what? Visible?
Yeah.
Yeah, they're generating a lot of energy, but it's through gravitational contraction. So they are luminous.
So then I'm assuming that when they do ignite, you get a large flash.
I think it's probably a fairly, gradual. Yeah, I don't think it's a sudden turn on. I think it's just, yeah. There must be visible because the star T Tauri is, you know, it's probably, I'm not sure it's visible with the naked eye, but it's, yeah, it's definitely visible in a telescope. So yeah, they're definitely, but a lot of them are obscured by the dust and gas in the circumstellar disk around them. So that can make them a bit hard to see. But yeah, but I'm not quite sure how quickly they turn on, whether it's a gradual process or a flash. Like the helium flash when a helium shell starts, I'm not sure. But, yeah, good question though. Any more questions?
That last chart you had up there, how does the stars like the crux fit into that?
So which star?
Oh, like the crux, the Southern Cross. Where would that fit into that?
Well, the Southern Cross is a constellation.
Yeah, but the four main stars.
Oh, the four main stars. Yeah, well, A Crux is the brightest star in the Southern Cross. I'm not quite sure, but it'd be somewhere in the middle here somewhere. That's a pretty powerful star. Yes. For instance, 2 is probably about 2 solar mass stars. That's probably Sirius, the brightest star in the sky. It's about 2 solar masses. So you can see it's only going to live for a quarter of the time that the sun does. But it's about 8 times the luminosity. So that's one of the reasons Sirius is so bright in the sky, is because it's 8 times brighter than the sun. Also, it's very close to us. It's only about 8 light years away, which is one of its closest stars. So that's the reason that it's such a bright star. Whereas Proxima Centauri, the closest star to us, at 4 light years away, we can't see it because it's a red dwarf, putting out 0.001% of the solar luminosity. Another example would be Rigel, the bright star Rigel in Orion. That's putting out about, it's probably about somewhere between these two, close to probably about 40 solar masses. It's putting out about 100,000 times as much energy as the sun. So that's 600 light years away, and yet it's still one of the brightest stars in the sky, even at that incredible distance. Yeah. Any other questions? Okay, thank you very much.